Okay, let's move on to sections 5.6 to 5.13, the final sections of chapter 5. Okay. If you look at the subtitles, vapor pressure diagrams, up to section 5.5, we deal with many different things about mixtures, right? Liquid vapor boundaries, solid liquid boundaries, what would happen to chemical potentials if you add a certain amount of solute, right? Something like that. From this section, we'll consider two different phases. First, liquid vapor phase boundary. How we can determine vapor pressure of gas as a function of composition. And can we draw a diagram which can represent that vapor pressure change as a function of composition? Okay? The next subtitle is temperature composition diagram. Here, the diagram is on pressure composition diagram. Okay? So, similarly, we can also draw temperature composition diagrams. Okay? So, these diagrams are basically for liquid vapor phase boundary. Okay? And we'll also introduce several non-common phase diagrams, such as liquid-liquid phase diagram and liquid-solid phase diagrams. Alright. Okay. So, in chapter 4, we learned about phase diagram. And especially that phase diagram was for one component system, right? For pure substance. What would happen if there are two substances, basically mixture? How does phase diagram of the mixture look like? Okay? So we'll consider phase diagram of simple mixture. So in chapter 4, when there is only one component, pure substance, and there is one phase, one stable phase, then according to phase rule, F is C minus P plus 2. If there is one component, C is 1, and one stable phase, P is 1, then the variance F is 2. So we can independently change temperature and pressure at the same time, right? Now, let's consider two-component system. There are two components. So C is 2. C equals 2. Okay? Then variance F is equal to 4 minus P. Okay? Then, if we fix the temperature, if the temperature is held constant, then the remaining variance is F 3 minus P, right? So, which has a maximum value of 2 for single phase, right? If P is 1, F prime is 2. Okay? And that variance of 2 represents pressure and composition. Okay? For two-component system, if we fix the temperature, then the remaining independent intensive variables are pressure and composition. Okay? So basically, for simple binary mixture, we can have phase diagrams of pressure as a function of composition. Okay? Or, if we fix the pressure instead of temperature, then we'll have temperature composition phase diagram. Okay? So, let's first follow this statement. Okay? We fix the temperature and we can have phase diagrams of pressure and composition. Alright, so there's a diagram here, which is called vapor pressure diagrams. We don't know why yet. Okay? Let's assume that we have a simple binary mixture, and those mixture form an ideal solution comprising two volatile liquids. Okay? Then, since this mixture is an ideal solution, both components A and B should follow Raoult's law, right? So PA should be equal to XA PA star, PB should be equal to XB PB star, right? Raoult's law. Okay? So total pressure of vapors should be equal to PA plus PB, right? Total pressure here in y-axis. PA plus PB is equal to XA PA star plus XB PB star. Okay? Since XA plus XB is equal to 1, we can replace XB by 1 minus XA, right? Then this expression can be rearranged as PB star plus PA star minus PB star times XA. So this formula basically shows the relation between total pressure P and XA composition. Okay? So if you plot P as a function of XA, since PA star or PB star is a constant, right? Vapor pressure of pure substance A and B, those are constants. Okay? So these two have linear relation. Okay? Total pressure as a function of composition XA. Here, you have to note that XA, mole fraction of A in the mixture, is for liquid, right? Mole fraction of A in the liquid of mixture, okay? So, from this equation, if mole fraction of XA is 0, then if XA is 0, P is equal to PB star, PB star here. If XA is 1, then P is PA star. It could be either this way or this way, but we just assume that A is more volatile than B. So PA star is larger than PB star. We just assume. Then the pressure composition diagram would look like this. Okay? Then, if these two materials are both volatile, they would evaporate, right? They would form vapors, vapor A, vapor B. Okay? And you can imagine that compositions of liquid and vapor in equilibrium are not same, right? If we have a certain composition, XA and XB, in the liquid, they would have some composition in the vapor. But those compositions of liquid and vapor would not be the same, right? If a certain material, for example, if A is more volatile, then it would more easily be evaporated. Then the composition of vapor for A would be larger than B, we can expect, right? Okay? So, if you recall, XA and XB are mole fractions in the liquid mixture. Okay? Let's denote mole fractions of gas in the mixture of gas as YA and YB. Okay? Then, from Dalton's law, YA is equal to PA over P, and YB is equal to PB over P. Right? Then, from this definition of YA, and from previous relations that we got for PA and P, we can express YA as a function of XA. Okay? Like this. And if you plot this, if you plot YA as a function of XA, you'll have this kind of diagram. Okay? This number 1, 2, 4, 10, 50 represents the ratio of vapor pressure of A over B as pure substance. Basically 1, 2, 4, 10 represents the PA star divided by PB star, meaning that A is more volatile. Then what we can find is that YA, when A is more volatile than B, YA is larger than XA. Right? Our assumption was right. If A is more volatile, there are more vapors than the other. Okay? So YA is larger than XA. Vapor is richer in more volatile component. Okay? And as we did for this, as we plotted total pressure as a function of mole fraction in the liquid mixture, we can also plot total pressure as a function of mole fraction in the gas. Okay? P as a function of YA. Okay? So using these equations, also in the equations in previous slide, we can have expression for P as a function of YA. You can do the derivation by yourself. Okay? And what we get is this. Looks like this. Okay? One thing which is very interesting is that when you saw this, let's use the whiteboard just for a while. So for pressure composition diagram, it looked like this, right? If A is more volatile than B, total pressure was like this. And the intercept here was PB star, here was PA star. Okay? If you do the same thing for total pressure as a function of mole fraction in the gas phase, the equation looks like this. P is equal to PA star, PB star over PA star plus PB star minus PA star YA. Okay, let's draw this. As you see in the diagram, it looks like this. Okay? And let's check the intercept here. If YA is 0, this part is removed and intercept is PB star. Right? If YA is 1, then PA star removed and intercept is PA star. Interesting, right? We draw total pressure as a function of mole fraction in the liquid phase and gas phase. The shape is different, but the intercepts are same. Okay? Then, what if we combine these two, right? And draw only one phase diagram, total pressure as a function of composition. Okay? And draw something like this. Same intersects and differentiate. Okay? That will be possible. Okay? So for example, if the mole fraction in the liquid phase is XA, for example here, this pressure represents the total vapor pressure when mole fraction of A in the liquid is XA, right? And if the total pressure is this number, then the mole fraction of A in the vapor would be YA, right? Like this. We can interpret this total diagram, something like this. Okay? Very simple. Then, instead of using mole fractions in the liquid or gas phase, let's combine it. Let's use x-axis of this diagram as total composition, ZA. ZA is total composition of A in the liquid and in the gas, totally, right? Okay. If you use just the common composition of A in the mixture, and we can simply interpret the meaning of total vapor pressure, mole fraction in the liquid phase, mole fraction in the gas phase, something like that. Interpretation is easy. Okay? So since we interpreted this diagram as I did, right? We can consider these lines as phase boundaries. Let's say Y. So this was XA, this YA. Okay. So when composition of in the liquid is XA, the total pressure is here, total vapor pressure. What if pressure is larger than this number? So for example here, pressure is larger than the vapor pressure of the gases. Then the vapors would be condensed, right? Which means that this area represents liquid phase, right? Larger pressure than the vapor pressure of the vapor. Okay? And when the pressure is P here, this position represents the composition of A in the vapor phase, right? What if pressure is smaller than this? If the outer pressure is smaller, then the material will evaporate more, right? So this area represents vapor phase. Okay? And similarly, the area in between this line and this curve would represent the area at which both liquid and vapor phase coexist. Okay? Right? When composition is XA in the liquid, vapor pressure is here, total vapor pressure. When total vapor pressure is here, the composition in the gas phase is here, YA. So this area basically represents the place at which both liquid and vapor coexist. Okay? Alright, let's do the interpretation of the diagram a little more. Alright. So we can denote the horizontal axis as overall composition ZA. And as I already explained, all points down the solid diagonal, okay, here, such as here, corresponds to a system under high pressure, higher pressure than the vapor pressure. So there's only liquid, okay. So in this area, ZA is equal to XA, since there is only liquid. All points on lower curve, lower than this blue line here, correspond to a system with low pressure, lower than the vapor pressure, right? So only vapor exists, okay? In that case, ZA over composition is equal to YA, okay? All right. And points between lines are systems where two phases coexist, liquid phase and vapor phase. All right. And let's see what would happen if we start from here, A, point A, and follow this vertical line from A to A4 here. A to A4 basically represents the lowering pressure, right? What if we lower the pressure over liquid? We can do it by simply doing this kind of experiment. Something like this. We put some liquid in the piston, okay? And we pull this piston to this direction. Simply increase the volume. That will decrease the pressure, right? So simply by this pulling out piston experiment, we can do this lowering of the pressure from A to A4. Let's see what happens. Okay. Let's start at point A. Here, only liquid exists. Okay. So we can go down up to A1. Okay. Now you reach A1, point A1. Okay. Then what happens is that it starts now that liquid and vapor phase coexist. Right? Liquid is in equilibrium with this vapor, and the composition of the liquid would be here, right? XA. And the composition at the same total vapor pressure of the sorry. At total vapor pressure P1, composition of vapor would be here, A1 prime, right? And this kind of horizontal line is called tie line. Okay? And you go down more. You reach here, A2 prime. Pressure is now P2. And when total vapor pressure is P2, composition of the liquid is here, A2, right? And the composition of vapor is A2 prime, right? Liquid and vapor are in equilibrium. Okay? Let's go more. You reached here, at the boundary. Pressure is now P3, lower pressure than before. Composition of the liquid is A3, composition of the vapor is A3 prime. Okay? Now, pretty much all the liquid are evaporated, right? And right after A3 prime, everything is vapor, right? So at A4, everything is vapor, and the composition of the vapor YA is equal to ZA here. Okay? You can interpret the simple pressure change of this pressure composition diagram. Okay, the same thing here. Okay. So, for the tie line, the horizontal line, if you recall, basically liquid and vapor are in equilibrium, they coexist. Then, can you have information about how much liquid are present and also how much vapor are present? Their relative ratio. Can you know? The answer is yes. Using this level rule. Level is very simple rule. If you have this kind of tie line, okay, the pressure is here, the liquid phase composition is here, vapor phase composition is here. So simply looking at this line, you can determine how much liquid are present and how much vapor are present using this rule. So just this rule is called the level rule. Now if you look at this rule, N alpha is number of moles of alpha phase, such as liquid, and beta is number of moles of beta phase, okay, such as vapor. L alpha is the length of this line, just length simply. L beta is this length. So if you know the length of these two separating lines, then you can determine the relative ratio of alpha and beta phase, liquid and vapor phase. Okay? The derivation is very simple. If number of moles of alpha phase is N alpha and number of moles of beta phase is N beta, the sum of that is total number of moles, N, right? And is N alpha plus N beta. Then the overall amount of A would be N times ZA, right? ZA is the overall composition of A. Okay? And NZA should be equal to N alpha XA, okay? Number of moles of, for example, liquid phase mole fraction, and N beta YA, number of moles in the gas phase and mole fraction in the gas phase. And that should be same as N alpha Z alpha and beta Z alpha, because Z represents overall composition, right? So if you rearrange this, you get this. N alpha XA minus ZA is equal to N beta ZA minus YA. XA minus ZA corresponds to XA minus ZA, this length. ZA minus YA. ZA minus YA represents this length. All you need is this length. Okay? Then you can determine relative amount of material in two different phases. Temperature composition diagram. When you first dealt with this phase diagram of simple binary mixture, we fixed temperature, right? And the other two intensive variables were pressure and composition. Now we can fix the pressure, right? Then the remaining two variables are, two variances are temperature and composition. So we can draw the same phase diagram for temperature and composition. Okay? And for simple binary mixture, if A is more volatile, temperature composition diagram looks like this. Okay? There are two boundaries. Okay? And you can understand this diagram simply, right? For example, this region, when temperature is really high, which means that it's vapor. Okay? This region, when temperature is low, liquid. And in between this blue and purple line, liquid and vapor coexist in equilibrium, right? Okay? Alright. The usefulness of this temperature composition diagram is that we can understand the distillation process you might do the distillation experiment in the class, in this room later, in the experimental classroom, right? We can understand the distillation process using this temperature composition diagram. Let's do it. Okay? Let's say we start from here, A1, at low temperature, so it's a liquid, okay? And we increase the temperature from A1 to here, A2, okay? So since A2 is the boundary, if the temperature reaches T2, the liquid would start boiling, right? It starts boiling, okay? And the composition of liquid at temperature T2 would be here. At T2, composition of the vapor would be here, right? Here. Okay? And what you do is you collect these boiling vapors, only this boiling vapor, and you condense it. Okay? Then the vapors with this composition would have lower temperature like this. Okay? Like this, for example, like here. And you increase the temperature again. It starts boil at A3, at T3, right? And at T3, composition of the vapor is here, A3 prime. And you collect the vapor again, and you condense it, like this. You do it again and again. Then what you get is that you started from here. Mole fraction of A1 is relatively low, like 0.2, something like that. And if you do this cycle again and again, what you reach is here. Mole fraction of A as 1. You basically get pure substance of A. Okay? That's the process of distillation. Okay? You collect the vapors, you condense it, and you evaporate again, condense it, something like that. You do it again and again, and you get basically pure substance. Okay? As shown here, you might be familiar with this figure, right? It shows the apparatus for fractional distillation. Alright. The thing is, most binary mixtures have the temperature composition diagram which look like this. This is the most case. But there are also exceptions. Some binary mixtures have somewhat weird temperature composition diagram, such as this. Some mixtures have this temperature composition diagram. It's a bit different from the previous one, right? Okay, and see what would happen if you do the some similar distillation process. Okay, let's start from here. A. You increase the temperature. Okay, it starts boil, and the composition of the liquid is here, composition of the vapor is here. Okay, then what you do is a little bit different from the previous distillation process. You do is vapor is removed. Okay, when you start here, it starts boil here. Okay, you remove the vapor, totally remove from the system. Then the remaining liquid would be richer in B, right? It would shift to the left, somewhere like this, right? Such as A3. Okay? And you boil it again. You increase the temperature. It starts boil, liquid and vapor. You remove the vapor again. And it will shift to the left to A4, something like that, right? You do it again and again, and it would reach here eventually, right? if you reach this point, whatever you do, if you increase the temperature or not, even though it boils, liquid and vapor composition are the same, right? Then, by distillation, you cannot separate the mixture, right? To separate the mixture, liquid and vapor phase should have different number of moles or different composition, right? Using that information, you can separate a certain type of material, more volatile one first, right? But at this point, liquid and vapor have same compositions, so you cannot separate the mixture. Okay? The mixture basically boils without changing the composition in the liquid and in the vapor. So this kind of point is called azeotrope. Azeotrope means boil without changing composition basically. Okay? So when azeotrope is reached, you cannot do separation by distillation. Okay? Similarly, there are also a lot of exceptions. Some mixtures have this kind of phase diagram. Okay? And this point is called azeotrope. Okay? Low boiling azeotrope. Okay, you can understand it similarly. Immiscible liquid. If you recall, liquid mixture, there were three different kinds: totally miscible ones, immiscible ones, such as water and oil, and partially miscible ones. Right? If you do distillation of two immiscible liquid A and B, such as oil and water, okay, what would happen? In reality, if you mix water and oil and let it stay, water would be at the bottom and oil would be at the top. But here, when you do distillation of two immiscible liquid, what you do is you strongly agitate the mixture, agitate the water-oil mixture. So so water is not at the bottom and oil is not at the top. They are mixed together continuously. Okay? Mixture is agitated. Okay? Then the situation is something like this, right? Both water and oil are open to the atmosphere. It's something like water and oil are separated like with this vertical barrier, right? Okay? Then what would happen? As you know, total vapor pressure should be vapor pressure of A plus vapor pressure of B. And if these two are not mixed together, and if you do agitation, mixing, continuous mixing, then they are separated something like this, then total pressure would be same as vapor pressure of A as pure form, and vapor pressure of B as pure form. Okay? Which means that if this total pressure reaches 1 atm, this solution starts boiling, right? And since total pressure is the sum of vapor pressure of A in the pure form and vapor pressure of B in the pure form, we could reach 1 atm at relatively low temperature, right? So, at relatively low temperature, we can boil this solution. Okay? That's the basis of steam distillation. Okay? steam distillation is something like a kind of distillation that we use basically water. If there is a certain organic compound which is not soluble in water, such as oil, right? And especially if that material is heat sensitive, if you heat the sample, it might decompose the sample. Then what you do is you mix it with something it cannot dissolve, immiscible ones, and you heat it up. Then at relatively low temperature, it starts boil. Okay? So for example, steam distillation. As I said, it is useful for heat sensitive organic compound. Okay? It's too small, right? Sorry. Heat sensitive organic compound. Let's see an example. For the mixture of phenylamine and water, okay, these two are immiscible, and the boiling point BP of phenylamine is 184 degrees C, and water is 100 degrees C. Okay, but if you mix these together, and if you agitate it continuously, and you heat the solution, this mixture starts boil at 98 degrees C at relatively low temperature, because even at this temperature, sum of vapor pressure of phenylamine and water reaches 1 atm. Okay, so at relatively low temperature, if you want to boil phenylamine, you have to heat it up to like 184 degrees C. But only at 98 degrees C, you can boil it, and you can possibly separate these two mixtures using steam distillation. Okay, this is the end of section 5.7. Okay, now let's move on to section 5.8. Liquid-liquid phase diagrams. Until now, especially for liquid-liquid phase behavior, we consider 2 out of 3 different liquid mixtures, right? Totally miscible ones and immiscible liquids. Now, we will consider partially miscible liquids and how their phase diagram looks like. Okay? If you look at the phase diagram of partially miscible liquid, it looks like this, right? This region P is equal to 1, so there's only one phase, right? Which means that 2 different liquids are totally mixed together, right? But here, there are 2 different phases, right? Because they are partially miscible. In this region, there are 2 different phases coexist, okay? And let's see what happens. So let's follow these 4 steps, okay? Let's start from here. For example, let's say that we only have A, okay? We'll consider the mixture of A and B, and first there is only A here, okay? And we add B to the solution, to the liquid A, okay? If there is only a small amount of B added to A, then they can mix completely together, right? It can dissolve completely. So there is single phase, right? P is equal to 1. there are large amount of A and there are small amount of B. So they can be mixed together. Okay? So we add more and more B. So above this point, okay, B no longer dissolves, right? A is totally saturated with B, and then there is another phase, okay, which is B saturated with A. Okay? The major phase is A saturated with B because there was only A at the beginning, and we add more and more amount of B, right? So the major phase is A saturated B, and if you add more B above this phase boundary, right, then B cannot be dissolved in A, right? And there are more B, there is another phase which has more B, right, which is B saturated with small amount of A. Okay? So in this region, that those two different phases are present. Okay? One of them is A saturated with B, the other is B with a small amount of A. Okay? And more, we add more B and above this phase boundary. Okay? Here, for example, then there are much more B now compared to A, right? So basically this x-axis is the mole fraction of B, right? So there are much more B compared to A. Then all of A can be dissolved in B. So now we are back to phase of number 1. Okay? They are totally miscible. Okay? In this region and also in this region, when one of these two material, A or B, is much more than the other, then they can be mixed together completely. But on the other hand, in this region, they are not mixed together. So there are two different phases. Okay? So here shows the representative example of a partially miscible liquid, especially their phase diagrams. Okay? Then, what if the mole fraction of B is here, A here? Then, as you remember, there are two different phases, A saturated with B, B saturated with A, and the relative amount of these two different phases can be determined by Lever rule, as we have learned, right? If you know the information about the length of this length and this length, we can determine the relative amount of each of these phases, right? As shown here, as shown in this example. Okay. So here, this example is for hexane and nitrobenzene. They form partially miscible mixture. And for example, if mole fraction of nitrobenzene is here, like 0.41 here, then if you know the information about this length, L alpha and L beta, then you can determine the relative ratio of these two different phases. One of them is hexane rich phase, the other is nitrobenzene rich phase. Okay? Since partially miscible liquid mixtures have phase diagram which looks like this, which means that if the temperature is above that, for example, for this mixture, if the temperature is above 300 degrees C, okay, then there's only one phase. Okay, so here's this, for this kind of partially miscible mixture, there is a certain temperature which is called critical solution temperature. Okay, that determines the highest temperature at which phase separation occurs. Because below this temperature we can have phase separation, right, in here, but above that we cannot have phase separation. Okay, so for this kind of phase diagram, especially for partially miscible ones, this temperature is the highest temperature at which phase separation can occur, and that is called upper critical solution temperature. Okay? if you might recall, when we considered the regular solution, remember, regular solution was a model system to describe the behavior of real solution, right? I believe that you remember. And when we dealt with regular solution, you might remember this kind of diagram. Gives energy of mixing as a function of composition, right? If you recall, there was a constant psi, and if psi is larger than 2, we encountered 2 minima of the Gibbs energy of mixing, which means that there is a phase separation, right? Similarly, Gibbs energy of mixing as a function of composition changes as a function of temperature. Okay? As you see, when the temperature is low, like here, there are these 2 minima, which represents the phase separation, right? Of 2 different phases, as we have saw here, right? But if the temperature is high, then there is no 2 minima, right? There's only 1 minima, which means that they are totally mixed together, right? Which corresponds to this, right? When temperature is low, we encounter phase separation, but when temperature is high, then there is no phase separation, right? Between 2 different liquid mixtures, okay? But not all partially miscible liquid have this kind of phase diagram. Some of them have this kind of phase diagram. Okay? It's totally opposite, right? So for this kind of phase diagram, we have lower critical solution temperature, right? Above this temperature, we experience phase separation, but below this, we do not have phase separation, right? Some systems, some mixtures have this kind of phase diagram. In that case, we have 2 critical solution temperatures, okay? Alright, this is the end of section 5.8. Let's move on to 5.9. Liquid-solid phase diagrams. Okay. We only consider the liquid-vapor phase diagram, and what we learned is azeotrope. Remember? Azeotrope is a certain composition at which we cannot separate the mixture by distillation, right? Because the composition of the liquid and the vapor was same at azeotropic point, right? Similar behavior happens for liquid-solid phase diagrams. Okay? So as you see, this shows an example of liquid-solid phase diagram of a certain mixture, A and B. Okay? And the temperature is much lower than the boiling temperature. Okay? If you look at the phase diagram, here in this region, only liquid phase present, okay? And P is equal to 1. So A and B are totally mixed together, completely, right? As totally miscible, perfectly miscible liquid mixture, okay? But here, in this region, is denoted as liquid plus A. At relatively low temperature, below this phase boundary, there is liquid mixture, but also some material of A is precipitated as solid. So in this region, liquid mixture and solid A are present together. Okay. Similarly, in this region, liquid mixture and solid B are present. Okay. And below this temperature, there is only solid. And P is equal to 2, which means that both A and B are present as solid at low temperatures. Okay? Okay, let's interpret the behavior of lowering the temperature. What happens? Okay, let's follow this transition from A1 to A5. Okay, let's see, at A1, at relatively high temperature, only liquid phase are present, right? They A and B are completely mixed together. Okay? We lower the temperature up to A2. Then system enters liquid plus B phase here, okay? Which means that there are liquid mixture and some B. Solid B comes out of solution. Okay? So let's go down more. Let's lower the temperature. For example, at A3, more solid B forms. Okay? And in this region, there are two different phases, right? Liquid mixture and solid B. And relative amount of each of these phases can be determined by level rule. If you know the relative length of this and this length, which is about equal, right? Which means that equal amounts of liquid mixture and B. Okay? Let's go down more to A4. Then less liquid, and finally after this point, there's only solid. Okay? Liquid now freezes into a two component system of A and B. Okay? Then if you look at the phase diagram here, there's an interesting point here which is called, denoted as E2. Okay? At this point, if you look at carefully, if you do this kind of temperature change, okay? For example, if you start from here and you lower the temperature through this point, then what happens is that at a single temperature, liquid phase changes to solid phase without experiencing these two different phases, right? So this kind of point, this kind of composition, especially at this composition, is called eutectic composition. Okay? And eutectic composition is the mixture with the lowest melting point, right? Melting point is here. But on this region, melting point is here, above that, right? So eutectic composition has the lowest melting point. Okay? And interestingly, liquid basically freezes at a single temperature with eutectic composition. Okay? They do not change composition as we encountered for azeotrope, right? For liquid vapor phase transition, at an azeotropic composition, if you remember, there was no change of composition between liquid and vapor. Similarly here, at this composition, liquid basically freezes into solid without changing composition, right? Same composition, maintaining the same composition. Okay? So liquid solid phase diagram have this interesting point called eutectic composition. Okay? So liquid with eutectic composition freezes at a single temperature, okay, without depositing A or B in advance of the freezing point. Okay. All right. So eutectic have a certain applications. So, for example, you see, like you might know what solder is, right? Solder has a eutectic composition, so we can easily melt or freeze the solder without changing the composition, something like that. And this eutectic formation happens in many binary alloy systems. There are many examples which have this eutectic formation. Okay, and we can determine this eutectic composition by many different types of experimental technique. Okay, for example, we can check use microscopy X-rays or NMR or something like that. Okay. At different composition, we check how a certain liquid or solid mixtures change in terms of microscopic nature or crystallographic nature or NMR. Okay. And usually, thermal analysis is used to build the eutectic phase diagram, as you have saw here. To make this kind of phase diagram, we usually do thermal analysis. What it means is that we do this kind of thing. We just change the temperature at a certain composition. Here, 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 something like that. We do it repeatedly, and we can build this kind of phase diagram. The principle of this thermal analysis to make eutectic phase diagram is shown in this figure. Okay. So you start from here at a relatively high temperature, okay, and you cool down, okay, and each of these lines represents different composition, okay. So, for example, here, this line, A1, A2, A3, A4, A5, this line corresponds to this line, okay? So, you start from A1 and you lower the temperature, okay? And above A2, as you see, the slope of this line changes, right? Which means that cooling gets slower compared to here. Because above A2, we are basically making solid B, right? Solid B is precipitated, and that precipitation is exothermic reaction. So because of that exothermic reaction, we are making basically heat. So because of that heat, the cooling gets slower compared to here. It's much steeper here, right? Slower, and above A4 here, finally we experience freezing, right? The freezing, basically temperature does not change, okay? Because freezing is physical phase transition, right? We do not experience temperature change at freezing, okay? And go down, something like that. Okay. We do that at different compositions again and again, okay? And especially at eutectic composition here, eutectic composition, okay? We do not experience this kind of precipitation, this kind of exothermic reaction. So we can have decrease in temperature and solidification, freezing at eutectic composition. So by doing this kind of thermal analysis at different composition, we can determine which composition has eutectic composition, okay? Alright, so we have seen several different types of liquid phase diagrams or liquid solid phase diagrams. There are also exceptions. There are many different types of phase diagrams. One example is reacting systems. Okay? A certain material do not just mix together, they react, they do chemical reaction. For example, gallium and arsenide. If we mix these two materials, they do chemical reaction and forms gallium arsenide. Okay, so if you mix 1 to 1 gallium and arsenide with 1 to 1 ratio, they totally form gallium arsenide. If you mix more gallium compared to arsenide, then all arsenide is consumed by this reaction, and some gallium is left, and we have gallium arsenide. So if you have this kind of reacting system, then we have this kind of phase diagram. Okay, here A, B are gallium and arsenide, and we have another composition C, which is gallium arsenide, right? So if there are more gallium, then all arsenide is consumed by this reaction. So we have phase diagram between gallium and gallium arsenide here. If there is more arsenide, then all the gallium is consumed by this reaction, and the remaining materials are arsenide and gallium arsenide, right? Gallium arsenide and gallium arsenide. So basically we have two phase diagrams combined together for this reacting system. Okay? Alright. There are also many other exceptions, such as incongruent melting. As you see here, the phase diagram of alloy Na2K is very complicated, right? Here is piece 1 as liquid, here is liquid plus solid K containing some Na, blah blah blah. So there are this kind of congruent melting, like phase diagram, shows that this mixture, Na2K, does not melt uniformly and just decompose into another substances in some cases, right? Some cases it presents as Na2K plus some solid, etc. So it's not important. So it just shows that there are very complicated phase diagrams of solid-liquid phase boundary. Okay, let's move on. So this is the end of section 5.9. Let's move on to 5.10, solvent activity. When we dealt with vapors, especially real gases, okay? If you remember, to describe real gas using ideal gas equation, right? Remember the Raoult's law, okay? We encountered a term called fugacity, right? Fugacity is an effective pressure, right, for real gases, and fugacity was used to describe deviations of real gas from perfect gas behavior. Okay, that's for gases. Okay. Similarly, to describe solvent, solvent has activities. Okay. So activities is something like effective concentration, effective concentration or effective mole fraction, because concentrations or mole fractions are terms used to describe the behavior of solvent, right? Okay. Okay, let's start from the general equation here. As you remember, this is the general forms to describe the behavior of solvent, right, in a solution. Okay, mu A is mu A star plus RT log PA over PA star. This is the general case. Okay, if the solution is ideal solution, then you can change this part with XA, right? This is the Raoult's law, ideal solution. Okay, and this is for ideal solution. And how about for real solution? Real solutions would have totally different equation or totally different behavior compared to ideal solution, right? But what if you want to use the same equation, very simple one, very simple equation, you want to use this equation to describe the behavior of real solution, okay, then you cannot use this XA, because this XA is used for the description of ideal solution, right? So instead of XA, we use different variable which is called activity or AA. Okay? So simply to use same equation to describe the behavior of real solution, we replace XA with AA. Okay? And AA is defined as PA over PA star for real solution. Okay? So as I mentioned, AA is a kind of effective mole fraction or effective concentration. Right? Because mole fraction can be changed to concentration. Okay? Okay. So let's see the limit of this equation. Okay? All solvents obey Rao's law as the concentration of the solute approaches zero. Right? In a solution, if the concentration of solute approaches zero, which means that there's only solvent, right? Pure solvent, then that should follow the Rao's law, right? And in this limit, activity of the solvent approaches the mole fraction, right? Because solvents should follow Rao's law. Okay? So if you represent this as an equation, not equation actually, which means that as XA approaches 1, okay, meaning that the concentration of solute approaches 0, then A activity approaches AXA, the mole fraction. Okay? And since activity is used to describe the real solution behavior, okay, there is difference between AA and XA. So to describe the difference, we can express it as AA is equal to gamma A XA, which is gamma is the activity coefficient, another coefficient, right? As we have done for Fugosity coefficient, right? Okay, which means that as XA approaches 1, okay, as XB approaches 0, right? Then gamma A, the coefficient, approaches 1, right? So since AA is equal to gamma A XA, if you put this in here, we have this expression, right? Mu A is equal to mu A star plus RT ln XA plus RT ln gamma A. So these two terms represent the behavior of an ideal solution, and this term basically shows the deviation of real solution from perfect ideal solution behavior. Okay. Okay. So here we describe the activity of solvent. Okay. How about solute? How can we describe the solute behavior of real solution? Okay. Okay. For ideal dilute solution, okay, which basically follows Henry's law. Okay, if you remember Henry's law, right? Henry's law is described as this equation: PV is equal to KV XV, right? Okay. Then chemical potential of solute can be represented as this, right? Mu B is equal to mu B star plus RT log PV over PV star. Okay, and since this solute satisfies Henry's law, if you put this PV into here, you get this expression, right? Okay. And here we define a new standard chemical potential as mu B star as here, these two terms. We just define a new standard chemical potential mu B naught as this. This new chemical potential is not same as the chemical potential at standard chemical potential we have encountered before. We just simply define. Then this mu B can be represented as mu B naught plus RT ln XB. Right? So for ideal dilute solution, we have this expression to describe the behavior of solute. Okay, mu B is equal to mu B naught plus RT ln XB. Very simple equation, which pretty much look like Rao's law, right? The difference is between mu B star and mu B naught, right? So this equation represents the ideal dilute solution. Then, if you want to use this same equation to describe the real solution, especially solute in a real solution, then you simply replace this XB by AB, activity of solute. Okay? And activity can be, for real solution, defined as PV over KB, right? Because we basically replace the XB by AB, right? XB is defined by PV over KB, right? So activity of solute is defined by PV over KB for real solution. Okay? Alright. Then, as we did for solvent, we can similarly define activity as gamma B times XB to describe the difference between mole fraction of B and activity of B, right? Okay? And we know that as concentration goes zero, the solute obeys Henry's law, right? So as concentration of concentration of B approaches zero, activity of solute approaches mole fraction of solute. Also, activity coefficient of solute approaches 1, right? Okay. Finally, activities in terms of molarity. Up to here, we expressed activities in terms of mole fraction, right? And mole fraction can easily be changed to concentration, right? In terms, especially molarities, right? So in some cases, we can describe chemical potential of solute as a function of molarity instead of mole fraction, okay? In this equation, mu B naught is not same as this one, okay? Because we changed the XB to molarity, so this number is different, okay? That's pretty much all. You can just ignore this part. Okay, so here this table 5.3 summarizes the activities of solvent and solute, right? As we have already described. Okay. Activities of regular solutions. I think that regular solution was a model system, right? If you remember, okay. Model system to describe the behavior of real gas, okay. Real solution. Sorry. So if you recall, Gibbs-Ellerjohn mixing for regular solution was given by this equation, right? Okay. Then let's see. Okay, for regular solution, Gibbs-Ellerjohn mixing is shown here. And to describe the activities of regular solution, the equation called modulus equation, which shows the basically activity coefficient of regular solution, gamma A and gamma B, both of which are represented as psi xb squared, psi xa squared. And let's see how. Okay? Alright. So, Gibbs-Ellerjohn mixing was described as nRT XA ln XA plus XB ln XB, right? For ideal solution, right? Okay? And we want to use the same expression for real solution. right? So we replace XA and XB with activity and activity here, right? Okay? And activity is denoted, basically defined as gamma X, right? AA is equal to gamma A XA, AB is equal to gamma B XB, okay? So if you put gamma X to A, these two activities, then you get this expression, okay? Then, if Margulis equation, according to Margulis equation, if activity coefficient can be described as this, psi xb square and psi xa square, then you can put these two here, okay? Log gamma A with psi xb square, log gamma B, psi xa square. Then you put these two here, and you can this, and if you rearrange this, you can simply have equation for regular solution. Okay? And from this, from the behavior, from basically the activities of regular solution, let's see the limit, if the limit is true, especially for when concentration of solvent is high or concentration is really low. If this regular solution behavior follows the Raoult's law or Henry's law. Okay? Alright. So from Margulis equation, activity, which is defined as gamma times mole fraction, should be equal to gamma mole fraction times E over psi xb square, because we define the gamma using this equation, right? Okay, here. Okay, and we can change xb by 1 minus xa, right? So activity of solvent A is represented by xa epsilon over psi 1 minus xa square. Okay? Then activity is basically defined as PA over PA star, right? PA over PA star. So we can express PA as this, right? Okay? And we can simply draw PA over PA star, or activity, as a function of composition. Okay? And let's see if this regular solution behavior follows the limit, Raoult's law or Henry's law. Okay? Let's see. When psi is equal to 0, then PA is equal to xa PA star. Ideal solution, right? Okay? Ideal solution behavior here. When psi is larger than 0, if you recall the regular solution part, it is endothermic mixing. Okay? Then PA over PA star behaves something like this, right? This number represents the psi, okay? The constant psi. Okay? In this case, the vapor pressure is larger than ideal solution. Right? Vapor pressure is larger than, this is ideal solution behavior, larger than ideal solution. Okay? Because the mixing is endothermic, okay? Which means that the mixing between solvent and solid is unfavorable. Right? When psi is smaller than 0, is exothermic mixing, right? or favorable solute-solvent interactions, right? In that case, PA or PA star is smaller than ideal gas behavior. Vapor pressure is smaller than ideal solution behavior. Okay. All right. Let's see two different limits. As XA approaches 1, then the regular solution, a model system for real solution, should approach Raoult's law, right? Let's see. If XA approaches 0, approaches 1, here, it all follows Raoult's law, right? Near here, right? When XA approaches 0, it's much smaller than 1. If XA is much smaller than 1, then you can basically ignore this XA. Okay? Then this equation looks like this. PA is equal to XA E psi PA star. Okay? And E psi and PA star, both of them are constant, right? So basically PA is constant times XA, which is Henry's law. Okay? So you can see that clearly that at these two different limits, Raoult's law and Henry's law. Okay. Alright, finally, ion activities. We only considered solution which contains neutral compound, right? What if there are ions, cations and anions in the solution? I briefly explain the ion, basically the difference between ion solution and neutral solutions. Okay, briefly, the main difference is here actually. Okay, the difference between real solution and ideal solution was because of different molecular interactions, right? For ideal solutions, which comprise very similar liquid, their interactions were similar to each other, right? But for real solutions, molecular interactions between A and A, B and B, and A and B are all different, right? So that difference in molecular interactions is an important parameter to determine the difference between real solution and ideal solution, right? How about ion solution, ionic solution, a solution containing ions? Ions, cations, and anions, they have charges, right? Plus charge, minus charge. And their interactions, their electrostatic interactions are much larger than interactions between neutral molecules, right? Plus minus interactions are much larger. Okay? So the behavior of solution with ions are much different from ideal solution. Right? Okay? So it's not really easy to describe the behavior of ionic solution. And to describe it, we can have similar approaches that we have used. For example, let's say that we have ions N plus and X minus in an ideal solution. Okay, then total Gibbs energy, molar Gibbs energy, should be Gibbs energy, basically molar Gibbs energy or chemical potential of plus ion and minus ion, right? Okay, this is equation for ideal solution comprising ions. Okay, for real solution, molar Gibbs energy should be also same as summation of chemical potential of cation and chemical potential of anion. Okay, and chemical potential of cation for real solution can be represented as chemical potential of cation for ideal solution plus RT Ln gamma plus, right? Okay, and chemical potential of anion can be represented as chemical potential of anion for ideal solution plus RT and then gamma minus. Okay? Which corresponds to molar Gibbs energy of ideal solution plus RT log gamma plus gamma minus. Okay? And if we define a mean activity coefficient gamma plus minus as basically root gamma plus gamma minus, then we can separate the contribution of cation and anion like this. Okay? So if you basically sum up these two together, then you can have same expression as this. If we assume that gamma plus minus new variable as gamma plus times gamma minus and square root. Okay? It's not easy, it's actually impossible to separate the effect, influence of each ion, cation and anion, but by using this new variable, we can separate the chemical potential of cation and chemical potential of anion. Okay? Similarly, for general ionic compound, MPXQ, we can have similar approaches and we can similarly separate the effect of cation and anion. Alright. So, as I mentioned, the interaction between this cation and anion is very large. Okay? They have very strong and very long range interactions. Okay? So the behavior of ionic solution is quite different from ideal solution. Okay? So to describe the ionic solution, we use the Debye-Hückel theory. So the Debye-Hückel theory shows basically means that overall the solution is electrically neutral because we have same number of cations and anions, right? But near any ion, there is an excess of ions of opposite charge. For example, if there is a positive ion here, then near positive ion, more negative ion will be present compared to other places, right? So this kind of behavior of ions is called ionic atmosphere. Okay? And using this Debye-Hückel theory, we can represent the activity coefficient of ions, gamma plus minus, as using this kind of equation. Okay? And this equation only holds at very low concentrations. Okay? If there are so many ions, it's totally impossible to describe the behavior of ionic solution. At very low concentration, even at very low concentration, since there are large amount of interactions between ions at long range, we can merely just describe the ionic solution behavior. So log gamma plus minus is represented as minus Z plus Z minus. Here Z represents the charge number for ions, and A is just the constant, and I is called ionic strength, which depends on the concentration and charge number. Okay? And if you just look at the result here, as you see, when concentration is really low, activity coefficient is close to 1, but when concentration is high, it's much smaller than 1, basically far from ideal solution behavior, right? So if you look at the result, okay, show x-axis is ionic strength and y-axis is activity coefficient of ions, right? As you see, when concentration is low, it fairly well matches well with the real behavior, but as concentrations gets larger, that this simple equation cannot really describe the behavior of real ionic solution. There are differences between this simple equation and real data, right? So to match it more well, then we introduce more variables, and then we can try to match the real experimental data and with this simple equation. Okay, but even so, at low concentration matches well, but at high concentration is not really match well with this simple equation. Okay, so I did not go into the details about this ionic behavior, but one thing important is this Debye-Hückel theory, limiting law, that ions have very strong and long-range interactions, so it's not really easy to describe it, and their behavior is quite different from ideal solution because of that that ionic interactions. Okay, so this is the end of chapter 5, and let's move on to chapter 6.